want to do this one for Zach because he's at home sick, and my boy number 24 averages 25 a game.
Number one in the heart.
Yeah, number one in my heart, and he's ready to go off against Newton anyway.
All right, so Zach, this first problem is dedicated to you.
Yeah.
All right.
Let's go, Zach.
All right. If we were to solve the following equation, x squared equals 9, what would you need to do to both sides of the equation? What would we need to do to solve this, guys?
You have to
Take the square root.
take the square root.
Darren, do you think Zach would have taken the square root?
I don't think so, honestly.
Zach, I believe in you, even though Darren doesn't. All right. So when we take the square root, so if I were to solve this by taking the square root, what happens when you take the square root to solve an equation? How many answers do you get? Two. You get 2. You get the positive and the negative. That is right. Plus or minus. Plus or minus. All right, so if we have a quadratic function, what would be the inverse operation? It's obviously square root. So the inverse of a quadratic is a square root function. All right, so let's investigate the quadratic. Sammy, do you think that Zach would like a quadratic function?
Yeah, Zach's a smart kid. He knows.
He knows. He knows all about the quadratic. All right. Okay. So, obviously Zach would tell us that if we squared -2, we get 4. If we squared -1, we get 1. If we square 0, we get 0. Square 1, you get 1. Square 2, you get 4. And so, no, Zach's all over that. So, then you graph it, and this gives us the parent graph of a quadratic function. And it looks like a parabola. I'm missing my points a little bit, and mine's a little lopsided, but you get the idea. All right. So, let's think about the inverse. What does the inverse? Well, what do you think Zach would tell us the inverse does to the x and y? It switches them. Yeah, that's right. Amanda thinks Zach would say it switches them. Okay?
Yeah,
So we switch them.
Shout out 2-4, baby.
So this would be 4 -2. 1 -1. 0 0 doesn't really look much different. Neither does 1 1. And 2 4 becomes 4 2. So this would be the inverse. The inverse of that function. So if we go to graph that, we've got 4 -2, 1 -1, 0 0, 1 1, and 4 2. Okay, before I even graph this in, let's look at this blue original function. Does it pass the vertical line test? Yes, which means this graph or this relation is a function. Does that blue original graph pass the horizontal line test? No, which means its inverse will not be a function. Is it 1-to-1? No, therefore it's not 1-to-1. So when I draw this inverse in, we can see it is not a function. The inverse fails the vertical line test. So, the inverse is not a function, which really kind of bothers me because I just used function notation, didn't I? I really don't like using function notation when it's not a function. But we'll call it this just for this example. Alright, so what did we notice about the inverse? It is not a function. And we could have known that before we even graphed it, because the original graph failed the horizontal line test. Alright, so let's go take a look at the domain of the original function, f of x. Well, that's a quadratic. And the domain of every quadratic is from -infinity to positive infinity. Matthew, what do you think Zach would tell us about the range of this original function.
It's gotta be 0 to infinity.
Yes. 0 to infinity. Thank you, Matthew. I think that's exactly what he would have said. Alright, so when we talk about the inverse switches the x and y, and we talked about this yesterday. So if we switch the x and y, and domain represents all the possible x values, and range represents all the possible y values, the inverse switches the domain and range. So if we look at this inverse, does it appear that the domain goes from 0 to infinity? Yeah. Here's the lowest x value. It goes forever right. And the range, it keeps going up, it keeps going down. The range goes from negative infinity to positive infinity. Okay, what would the equation of the inverse be? Alright, let's do a little algebra. Let's start off with our original function, f of x. I'm just going to call that y equals x squared. To find an inverse, what is step 1? Switch the x and y. Let's do it. So let's make it x equals y squared. Step 2, what is step 2? Take the square root on this problem. Solve for y. When we take a square root, we get a positive and a negative. So the inverse of the quadratic is plus or minus square root of x. Square root of x is the square root function. Do y'all see the square root up, the positive one? And the square root down, the negative one? Do you see it? Let me do it with highlighter instead. Okay? The square root up is the positive one. It's right here. And the square root down is the negative one. It's down here. And together they make the inverse of the quadratic. Alright. So far so good? Alright, let's flip over to the back. Alright. Now we're going to look at the reverse. So if we were to solve this square root question, square root of x equals 2, what would you need to do to both sides of the equation in order to solve? Square. We would square both sides. So if I were to square both sides, how many solutions do I get? Well, 2 squared is 4. That's it. I just get the number 4, so I only get one solution. So this time we're not going to have that plus or minus. We're just going to get the 1. So if we have a square root function, the inverse of that would be a square. In this case, it's going to give us a quadratic function. Math quiz Monday, that's right. December 5th, last one. You ready? Back? Alright. Square root function. So we're going to take the square roots. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. And then we're going to graph this square root function. And it gives us the eyebrow up. It will be. But when we think about the inverse is just going to switch them, isn't it? So the inverse is going to give us 0, 0, 1, 1, but this one gives us this, 2, 4. So you're right, it is the quadratic, but it's only half of it. Yeah. So what does the inverse look like? It looks like half that quadratic. Now let's investigate why. So if we look back at our original function, this blue graph for the g of x, the domain goes from 0 to infinity, and the range also goes from 0 to infinity. So when I swap those to get the inverse, it doesn't look any different, does it? The domain, well, if I swap, it looks the same. And the range, if I swap, it looks the same. Now we're going to do one in a minute that looks different so you can actually see what's going on. So this said, what would the equation of the inverse of f of x look like? So if this should be g of x. If this is our function, g of x, we can say it's y equals the square root of x. We switch the x and y to solve. And then we would square both sides. X squared equals the inverse. But we know that this is the whole parabola. But we can look at our graph and tell it's not the whole parabola, it's only this half. So when we do inverses of square roots, it's going to give us quadratics. But we can't have both halves. So what we do is restrict the domain. So whatever the range was of the original function becomes the restricted domain. So the inverse of g of x is that x squared, which we just got right here, but you must give the domain restriction from 0 to infinity. We don't get to do the left side of this graph. We only get to do the right. And where we get this restriction from, this restriction comes from here. The range of the original function becomes the domain restriction on the inverse.
I was looking at the graph.
The range of the original becomes the domain restriction on the inverse. Okay, so let's look at some of these. The first one we have is a parabola. The second one we have is the square root. So we've got quadratic, square root. Alright, so if we think about this one, this is a quadratic whose vertex is down here at -4 and it's opening up, so it would look something like that. So what is the domain of that function?
Negative infinity to infinity.
It is. And what is the range? -4 to infinity. So when we think about its inverse, those are going to swap. So the domain is now -4 to infinity. And the range is now -infinity to +infinity. Because we switch the x and y's, we switch the domain and range. And now let's found it algebraically. So we switch the x and y and solve for y. So you talk me through it. What would Zach say we do first?
Hey, Zach would say do x plus 4.
We would do the +4. Very good.
Good job, Zach. Good job,
Davis
Zach.
said Zach would say we do x plus 4. Okay, and then we would take the square root of both sides. Now, when you do the square root, you get plus and minus. And that is our inverse. And the domain of this inverse would go from -4 to infinity. Now, what this ends up being is, go back to -4, and it goes eyebrow up, eyebrow down. And y'all remember, we talked about how that is a reflection over this y equals x line. If I had drawn it better, it would look more like a reflection. Alright, let's do a quick think about what this graph would look like. This one has the vertex here at 4, 0, and it's eyebrow up. It's a square root function opening up. So the domain of this is from 4 to infinity, and the range of this one is from 0 to infinity. So its inverse would have a domain of 0 to infinity, and it would have a range of 4 to infinity. All right, so let's find it. We switch the x and y, and we solve for y. So guys, what do I have to do first? Square both sides. So that gives us x squared equals y minus 4, and then we just add 4.
4.
And that is the inverse. But
Are we gonna have to grab these?
when we do it, this domain restriction must be listed for these. Must be. The domain is restricted from 0 to infinity because it is only this side of the graph. It is not both sides. So you must have both parts.
When you're doing it alphabetically, when you're doing it alphabetically.
Whenever you list the inverse of a square root function, you have to give that restriction on the domain.
But it's included in the answer.
It is included in the algebraic answer, yes. All right. Well, Zach, we've missed having you here today, buddy. Anybody else want to say a word to Zach?
Go to.
All right. Hope you feel better.